The threat includes Mount Rainier, which scientists continually monitor for activity. New at 6, KOMO meteorologist George Waldenberger spoke with a geophysicist about what she's been observing.
A deep, resonant rumble rolled through the Cascade Range in the early hours of the morning, shaking windows and sending startled residents to their doorsteps. It wasn't the sharp, jolting motion of a typical earthquake that had people uneasy, but rather a sustained vibration that seemed to pulse from deep beneath the earth. Mount Rainier, the towering ice-capped stratovolcano southeast of Seattle, had awakened with a series of seismic and thermal events so unusual that geologists immediately issued a rare red alert. The mountain, often admired for its breathtaking beauty, had suddenly reminded everyone that it is not merely a scenic landmark, but a colossal geological force, with the capacity to alter landscapes and lives in a matter of hours. Before we start, smash the like and subscribe buttons for more updates. The chain of events began subtly, almost deceptively. A week earlier, sensitive instruments around Rainier began recording small harmonic tremors, low-frequency seismic signals that differ from ordinary tectonic earthquakes. These tremors often suggest that masses are moving through underground conduits. By themselves, these signals weren't enough to cause alarm. However, when thermal sensors registered sudden spikes in temperature along the upper slopes and within the summit crater, volcanologists knew something significant was happening beneath the snow and ice. The increase wasn't gradual. It was abrupt, indicating a rapid shift in subsurface conditions. As the tremors intensified, the network of GPS stations installed around the volcano detected measurable ground deformation. The slopes were bulging, albeit subtly, a sign that pressure was building below. Such inflation of the mountain's flanks is one of the most telling indicators that magma is rising or that geothermal activity is becoming more forceful. The mountain seemed to be breathing, slowly then more urgently, while its icy crown began releasing wisps of steam visible to anyone with a clear view of the summit. This combination of seismic unrest, rapid heating, and surface deformation forced geologists to escalate their monitoring. When a fresh cluster of earthquakes struck just beneath the summit at shallow depths, the data painted a picture too consistent with pre-eruptive patterns to be ignored. These quakes were not powerful in magnitude, but they were shallow, sharp, and frequent, signaling brittle rock fracturing under the pressure of rising materials. The moment of confirmation came when airborne thermal imaging detected new fumaroles, vents spewing hot gases, emerging along the summit crater rim. Some of these were areas that had been dormant for decades, now glowing with heat. Gases rich in sulfur dioxide and carbon dioxide, both byproducts of magma degassing, were suddenly spiking in concentration. This was the kind of data that volcanologists dread because it speaks to fresh magma interacting with the surface environment. Within hours of confirming these readings, the U.S. Geological Survey moved Rainier's alert level to red, the highest possible, signaling that an eruption could be imminent or already underway. Mount Rainier is not just another volcano. It is considered one of the most dangerous in the world due to its immense ice cover and proximity to heavily populated areas. Unlike smaller volcanoes, Rainier's flanks are draped with massive glaciers that could melt rapidly if exposed to intense volcanic heat. The sudden release of meltwater could trigger lahars, volcanic mudflows capable of tearing through valleys at highway speeds. Past lahars from Rainier have traveled for miles, burying landscapes under meters of debris and sediment. Modern hazard maps show that entire communities lie in the direct path of such flows, making any unrest here a matter of grave concern. As scientists pored over the data, the scope of the unfolding event became increasingly clear. The unusual nature of the tremors suggested a significant movement of magma at relatively shallow depths, far closer to the surface than it had been in decades. While Rainier has experienced seismic swarms before, the current swarm was paired with visible surface changes, an escalation that dramatically shifted the risk profile. Satellite radar imaging confirmed that certain areas near the summit had uplifted by several centimeters in a matter of days, an extraordinary rate for such a massive edifice. The temperature readings were equally alarming. Snowfields that had been frozen solid were showing signs of rapid melting from below, creating meltwater channels that snaked through crevasses. In some places, steam plumes carried the faint odor of sulfur downwind, a sensory reminder of the chemistry churning beneath the mountain. Scientists warned that even without a full eruption, such heating could destabilize the glaciers, potentially causing ice collapses, and avalanches that could mix with volcanic debris to create destructive flows. The red alert was not issued lightly. For geologists, raising the status to the highest level requires multiple, corroborating lines of evidence that the volcano is entering a critical phase. Here, the convergence of data points, intense seismicity, ground deformation, heightened gas emissions, new fumaroles, rapid heating, and visual signs of summit activity left little room for doubt. Each of these indicators alone could be explained by minor fluctuations in volcanic systems, but together they formed a cohesive and troubling picture. Part of the urgency came from Rainier's unique geological makeup. The volcano is composed of layers of andesite and dacite lava, along with older, weaker hydrothermally altered rock that is prone to crumbling when destabilized. This means that intense internal pressure or heating can trigger not only explosive eruptions, but also catastrophic slope failures. In the worst-case scenario, a large section of the volcano's flank could collapse, releasing a massive lahar that would race down river valleys toward towns and cities. Such a possibility is not hypothetical. Geological records show that similar collapses have happened before in Rainier's history, reshaping the surrounding terrain in a matter of hours. Scientists monitoring the situation used every tool at their disposal. Arrays of seismometers tracked the changing frequency and depth of the quakes. Gas sensors on the slopes recorded minute-by-minute variations in emissions, helping to pinpoint the movement of magma. Drones equipped with infrared cameras flew dangerous reconnaissance missions into the summit area, relaying real-time images of steaming vents and newly exposed rock faces where snow and ice had vanished. Even from high altitude, the heat signatures were unmistakable. Hot zones spreading outward from the central crater, as if the volcano were radiating energy into its frozen shell. The surrounding environment responded in subtle but telling ways. Wildlife that normally frequented the upper slopes began moving downslope, away from the steaming vents and unstable snowfields. Small streams fed by glacial melt turned cloudy with fine sediment, a sign that the heat was disrupting the ice and grinding rock beneath. The air in certain valleys took on a faint metallic tang, the result of volcanic gases drifting on the wind. These changes were the kind that local residents might overlook individually, but together they painted a picture of a mountain shifting into a new and volatile state. The human dimension of the alert loomed large in scientific discussions. Rainier's slopes and surrounding valleys are home to thousands of people, with major cities like Tacoma and Seattle within range of volcanic hazards. While an explosive eruption could send ash high into the atmosphere, disrupting air travel and blanketing communities, the most immediate danger was from lahars. The geology of the region funnels these flows into well-defined channels, but those channels run directly through populated areas. Historical evidence shows that lahars from Rainier have reached as far as Puget Sound in the past. With the current signs of increased heat and possible glacial destabilization, the potential for such flows was more than theoretical. The red alert served as both a scientific declaration and a warning to anyone familiar with the mountain's past. Geologists stress that Rainier has not produced a major eruption in over a century, but that this dormancy is not an indicator of safety. In fact, long periods of quiet can allow significant amounts of magma and gas to accumulate within a volcano's plumbing system, increasing the likelihood that the next eruptive phase could be particularly energetic. The patterns now emerging, rapid heating, new gas vents, seismic swarms, fit the template of a system transitioning from quiet to active. One of the most striking aspects of the unfolding events was how swiftly the situation developed. Days before the alert, the mountain appeared serene, its glaciers gleaming under the summer sun. Then, almost imperceptibly at first, subtle atmospheric plumes began rising from the summit, visible only in certain light. By the time these plumes were clearly visible from nearby towns, the mountain's internal state had already changed drastically. Such a rapid progression left little room for gradual escalation in the alert level. Instead, scientists had to act decisively once the critical thresholds were met. The broader geological implications were immense. Rainier sits atop a complex subduction zone environment, where the Juan de Fuca plate dives beneath the North American plate. This tectonic setting feeds magma into the Cascade volcanoes, but it also means that seismic and volcanic hazards are intertwined. An episode of unrest at one major volcano raises questions about the state of others in the arc. While each volcano operates on its own timetable, shared deep magma sources and tectonic stresses can sometimes create regional patterns of activity. Monitoring Rainier thus became part of a larger watch over the entire Cascade Range. The red alert at Rainier also underscored the challenges of forecasting volcanic behavior. Even with decades of research, every volcano has its own personality, shaped by unique geological structures and histories. Rainier's vast ice cover complicates matters further, masking some surface changes and making others, like steam plumes, look more dramatic than they might on a bare rock summit. This means that interpreting the signals requires not only raw data but also expert judgment honed over years of studying the mountain's quirks. Still, the convergence of so many warning signs left little ambiguity. In scientific terms, the probability of an eruption had risen sharply. In human terms, the mountain was sending a clear message. Something significant was unfolding beneath its icy crown. The decision to issue a red alert was not about predicting an exact moment of eruption, but about acknowledging that the system had entered a phase where rapid, hazardous changes were possible at any time. From the vantage point of those watching the summit, the mountain now appeared subtly different. The ice near the crater rim had begun to sag in places, warped by the heat beneath. New discolorations marked the snow where mineral-rich steam had settled, staining it in shades of yellow and rust. Small avalanches cascaded down the upper slopes more frequently than before, suggesting that internal vibrations were loosening ice and rock. Each change, though small in isolation, added to the sense of momentum, an unstoppable process building toward a climax. Deep within Rainier's structure, molten rock was likely forcing its way upward, fracturing overlying rock and releasing volatile gases as pressure dropped. These gases, trapped under immense pressure at depth, expand violently when given space, driving the explosive force of eruptions. The detection of increased sulfur dioxide emissions indicated that this degassing was already underway, with magma potentially within a few kilometers of the surface. The mountain's glaciers, beautiful and ancient, were now potential fuel for disaster, their frozen mass a volatile partner to the heat rising from below. For the scientists involved, the red alert was both a technical milestone and an emotional moment. Many had devoted their careers to studying Rainier, fully aware of its destructive potential, but also drawn to its majesty. To see it entering such an unstable phase was both exhilarating and sobering, a reminder that nature's most awe-inspiring landscapes are also its most formidable forces. The mountain had shifted from dormant beauty to active threat, and every new reading from its flanks now carried the weight of possible catastrophe. From the lowlands, the mountain still looked serene to the untrained eye. But those who understood the language of geology knew that this was the deceptive calm before whatever came next. Instruments continued to capture the restless heartbeat of the volcano, a rhythm that had quickened and grown more irregular. The air above the summit shimmered with heat, a silent testament to the forces building within. This was the moment when Rainier was no longer a distant backdrop to daily life, but an active participant in the region's unfolding story. The red alert was not just a scientific designation, it was the recognition that the mountain had entered a dangerous phase, one that demanded vigilance, preparation, and respect for the raw power hidden within its snowy slopes. The events of the past days had made one thing undeniable. Mount Rainier was awake, and the world around it was watching closely, aware that the next movement from deep within could transform the landscape in ways both breathtaking and terrifying. In the hours following the issuance of the red alert, Mount Rainier's presence seemed to dominate the horizon with a weight it hadn't carried in living memory. The snow-draped peak stood luminous against the sky, yet beneath its veneer of stillness, geophysical changes were accelerating. From high-altitude monitoring aircraft, scientists observed faint but persistent columns of vapor rising from several points along the summit ridge. These columns wavered in the wind, thin at their bases, and widening as they dispersed, carrying with them volcanic gases that instrumentation confirmed were rich in acidic compounds. The distribution of these plumes indicated that the heat source below was not isolated to one conduit. Instead, several fracture systems and vents were active, each acting as a release point for the pressure building below. The shifting chemistry of the gases being emitted offered additional clues about the processes unfolding underground. Initially, the steam was accompanied by high ratios of carbon dioxide to sulfur dioxide, a signal often associated with deep magma movement before it nears the surface. As hours passed, the ratio began to invert, with sulfur dioxide levels rising sharply, a hallmark of magma degassing at shallower depths. This transition meant that molten material was likely approaching zones within the volcano's structure where contact with groundwater or glacial melt could trigger sudden phreatic explosions, bursts of steam-driven force that can occur without warning. Meanwhile, seismic records captured a new pattern: volcanic tremor, a constant low-frequency vibration distinct from the earlier discrete earthquakes. This type of tremor often signifies the sustained movement of magma or volcanic fluids in a confined space. Unlike the sharp jolt of a tectonic quake, volcanic tremor is more like an unbroken hum, sometimes persisting for hours or days. Its onset suggested that the system was no longer in a purely preparatory phase. It was actively mobilizing. The tremor also began to migrate slightly down the slopes, indicating that pathways of molten rock and gas were evolving, possibly branching into new areas of the volcanic edifice. Surface observations confirmed the subsurface changes. Climbers who had been on the mountain earlier in the week reported that snowfields near the summit had developed unexpected sinkholes, their rims steaming and their interiors revealing dark, thawed rock. These features, absent mere days ago, were clear evidence that heat was penetrating upward through the thick ice cover. Such melt features were not only geological curiosities, they were also hazards, capable of collapsing without warning and swallowing anything in their vicinity. As the situation progressed, satellite imagery revealed subtle but widespread alterations to the summit crater's shape. What had been a relatively symmetrical ice rim now showed slight sagging on its eastern side, a deformation that hinted at localized weakening of the underlying rock. This deformation, paired with radar-measured uplift in other sections, painted a picture of uneven internal pressure, with some sectors swelling while others subsided. Such imbalances can destabilize the structural integrity of a volcano's peak, especially when the flanks are composed of hydrothermally weakened rock, as Rainier's are. Deep beneath the mountain, molten rock was likely advancing through dikes and sills, exploiting pre-existing fractures and generating new ones in the process. As these molten pathways expanded, they would have been pushing aside rock, heating groundwater, and altering the internal plumbing of the volcano. Hydrothermal systems that had been stable for decades were now being disrupted, potentially leading to rapid shifts in pressure that could manifest at the surface as gas bursts, geyser-like expulsions, or even flank eruptions far from the summit. The behavior of the glaciers covering Rainier became another focal point of concern. Glaciologists monitoring the Emmons and Nisqually glaciers reported that crevasse patterns had begun changing in ways not attributable to seasonal melt alone. Some cracks widened at alarming rates, while others appeared in entirely new alignments, following patterns that matched the directions of underlying ground deformation. The glaciers, long thought of as static ice masses, were in fact responding dynamically to the shifts in the mountain beneath them. In certain areas, meltwater was pooling within the ice rather than draining away, creating reservoirs that could, if suddenly released, contribute to the formation of lahars even without a direct eruption. While instruments provided the most precise measurements, human senses could also detect the shift in the mountain's character. Rangers stationed in high camps noted a subtle but persistent rumble beneath their feet, like the muted resonance of distant machinery. In the valleys below, the sound was inaudible, but the visual cues were becoming undeniable. On clear mornings, the steam rising from Rainier was visible from miles away, its plumes catching the early light and tracing faint trails across the sky. These were not the sporadic wisps of past years. They were continuous, rising steadily and hinting at the relentless energy being vented from within. The composition of the steam was also significant. Samples collected by specialized aircraft contained traces of hydrochloric acid and fine mineral particles. The acid formed when volcanic gases interacted with water vapor, and the mineral particles suggested that fragments of rock were being pulverized and carried aloft within the steam itself. These microscopic grains were like forensic evidence, each telling a part of the story of mechanical and chemical processes grinding away inside the volcano. In the context of Rainier's geological history, such signs were particularly striking. The mountain has experienced numerous phases of activity over hundreds of thousands of years, and many of its most dramatic changes have been the result of interactions between magma and the vast ice mantle it carries. Each time molten rock has pushed upward in the past, the outcome has depended on the balance between internal pressure, surface stability, and the sheer volume of ice available to melt. In this case, with the mountain's glaciers currently more fractured than in previous decades due to climate-related thinning, the potential pathways for meltwater to reach and mix with magma were greater than in earlier cycles. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Mount Rainier's current activity? We want to hear from you. Thank you for watching, and see you next time.